The final discussion we have to have from chapter 22 is on the temperature dependence of delta G. This is something that you kind of looked at in lab already. You made some approximations and some assumptions, and now we're going to look at testing them directly. Now, unfortunately, we're not going to be going over the full entire derivation of this equation, this important equation, but this is the integrated form. So we're just going to kind of go over it. And you're going to trust me that in terms of where it came from. So it's the integrated form of the Gibbs-Helmholtz equation. So in your reading, you'll see there's this Gibbs-Helmholtz equation. And the reason it's called that is because it relates Gibbs energy and Helmholtz energy. And that relationship is expressed through this temperature dependence of G, okay? This integrated form is all we really need, though, to be able to calculate delta G at a different temperature. This is the formal way to do it, calculate delta G at a different temperature. So say you knew delta G at one temperature, such as a table temperature, okay? What you need to get delta G at a different temperature is you need to know what those temperatures are, and you need to know how H varies with temperature. So what ends up happening is you can do a lot of a lot of modeling with constant pressure heat capacity to get how delta H changes with temperature. If you go back and look at your notes, that's something that we've already kind of looked at already, how H could possibly have temperature dependence. And if you figure out what that temperature dependence is, you divide by T squared, you integrate, and then you can solve for this delta G at a different temperature. On your quiz, I'm going to give you a problem like this where I give you H of T already done, and I'll give you this delta G at a given temperature. And so you'll have some practice of actually enacting this exercise and solving for an unknown delta G at a different temperature, okay, relative to unknown delta G at a set temperature. It makes sense that delta G changes with temperature because we know that if we're thinking about an isobaric and an isothermal situation, like getting to a temperature and then staying there isothermally, right? We know that equilibrium can be shifted around based off of temperature from our general chemistry sort of knowledge. And so if equilibrium is being shifted around, then what side is favored and what side is spontaneous in terms of the motion of the particles in that chemical system, what side is favored must be changing, and so delta G must be changing as well. All right. So I don't really have a lot to say about this besides know this form and know how to use it and realize that this is the formal way of getting G at a different temperature. All right. To show you what you did in lab and to relate this to things that you did even in general chemistry, let's make some assumptions. So let's take this and let's let T1 be our standard temperature, like from a table. Remember, there's no such thing as a standard temp. It's really like your table temp. But what I'm really referring to in terms of standard temp is then we know we're at standard conditions, and delta G is equal to delta G naught is equal to delta G at T1. All right. So this now is delta G that we can get from that table procedure that we know how to enact. Well, let's make one last important assumption. Let's say that delta H is not a function of T, and let's say that it's constant. All right. So we're going to call delta H of T just delta H. And we're going to say that over this temperature range, let's pretend delta H is constant. Now remember, this was a main assumption that you made, or was one of the main assumptions that you made when you did your lab and you calculated G at different temperature. So let's see what happens. On the right-hand side here, this delta H, which now becomes, that was a function of temperature. It's no longer a function of temperature. If we look at it there then, if it's a constant for this temperature change, we're going to be able to pull it out front, all right? We're going to have an integral to do on the inside here, or left over here, and it looks like the integral of negative 1 over t squared dt, and we know how to enact that integral. So let's go ahead and write that next step down. Right here, we're going to have delta G at my new temperature, away from the table temperature I'm trying to get to, right? This is going to be delta G naught, standard value taken from that table, and this T1 is the table temperature, usually 298.15 Kelvin, okay? Over here, what I'm going to have is my delta H brought out in front. All right. Well, wait a second. If this is constant for all these temperatures and this guy is analyzed at the standard temperature, then this delta H must be a delta H naught that I could also get from that table, right? Because if it doesn't have any temperature dependence, I might as well use the table temperature and figure out what it is. Okay. The negative ends up canceling with the negative 1 involved in the integration here. And fill in the gaps with this integration, but what you essentially get is 1 over T2 minus 1 over T1. And like I said, make sure that you can fill in the gaps there in case I ask you to do it for homework. Okay. So then we have this set system, right? And what we really want to know is, okay, so what is delta G at T2? So let's go ahead and let's start to combine some terms. With our approximations, we have this complicated Gibbs-Helmholtz equation, the integrated form. It starts to reduce down when we make some assumptions, okay? So let's just take this and let's write it as delta G of T2 over T2 looks like delta H naught of T2, delta H naught over T2 minus delta H naught over T1 minus delta G naught over T1, okay? And we see that there's some combinations we can do here, things that have a like denominator. So on the right-hand side, let's manipulate further. This looks like delta H naught over T2 minus, right? Let's pull out the negative sign, all right? Delta H naught plus delta G naught over T1, right? Ooh, I think I made a sign error. So when I brought this guy over, this should be a plus, and this guy, it should be a minus. Please correct that in your notes. Okay. All right. So then how does this help us? Well, remember that for a set temperature, if we're talking about delta G and the important delta G that deals with isothermal isobaric situations, at that temperature associated with the table, delta G naught is equal to delta H naught minus T delta S naught. So that's a substitution that we can make in there, right? And that's true for all those table situations. And are we talking about a table situation? Yep, that naught is up there. So let's make that substitution. Let's leave the left-hand side alone. We're gonna have delta H naught over T2 minus, right? On the inside here, we're gonna have delta H naught minus delta H naught plus T1 delta S naught. All of this is divided by T1. So if we make that substitution that we talked about, we now see that on the inside of that parentheses, that parenthetical term, there's a delta H naught and there's a minus delta H naught. So these guys cancel. There's a T1 here. Now in the denominator, that's going to cancel the T1 there. And what we end up with is a delta S naught, okay? So now to finish off this problem, just to kind of rewrite what we have, we're left with, after our manipulations, a delta S naught on this side. So what do we do to solve for delta G at our new temperature? Delta G at our new temperature is equal to, okay, I'm going to multiply through by T2. The T2 hits that T2, and this becomes delta H naught, all right? There's no temperature here, so this becomes T2 delta S naught, okay? So what you did in your lab, which assumed that H did not have temperature dependence, is to get delta G at a different temperature. What you found was your delta H naught, your delta S naught. You assume that both were temperature independent, and then you just use T as a variable. This is not always correct. Remember the assumptions that led to this? The assumptions that led to this was that there was no temperature dependence here. That first term that we looked at, the integrated form of the Gibbs-Helmholtz equation, that is the correct way to go about analyzing the temperature dependence of G and how spontaneity for isobaric and isothermal processes might change with temperature. This works only when delta H naught is temperature independent, okay? So hopefully that clears that up. Again, not a ton of derivations here. Know how to use these equations, know how to go from that integrated form to this form in case I ever ask you to do so, but kind of realize then where that approximation that we were using earlier in the semester comes from. And it's kind of nice to see an equation where we can recover this form from a more complicated sort of expression.